In section 5.7, we're going to look at integrals resulting in inverse trigonometric functions. What I'd like to do to begin with is to come up with the formulas, and then we'll look at 3 examples. Suppose I start off by saying y is arcsine of x over a. Let's find y prime. We explored this a little bit in chapter 3, but let's go back over it. So in order to find this derivative, what we're going to do is start by taking the sine of both sides. So I have sine of y, sine of arcsine, those are inverse functions, so they'll cancel. So sine of y equals x over a. Now I'm going to differentiate. The derivative of sine y with respect to x, I'm going to use the chain rule. So we'll have cosine of y times the derivative of y, dy dx. On the right-hand side, the 1 over a is a constant. The derivative of x is just 1. So dy dx is equal to 1 over a times cosine y. Divide both sides by cosine y. If I use a Pythagorean identity now, sine squared y plus cosine squared y equals 1, then cosine squared y is 1 minus sine squared y. So cosine of y is either positive or negative square root of 1 minus sine squared y. We're going to use the positive square root. That will work in the portion of the domain where cosine is positive. So that'll be for angles or for values of y between negative pi over 2 and pi over 2. And earlier we said that sine of y is x over a, so I can write cosine of y is the square root of 1 minus x over a squared. I'm going to just simplify that a little bit more. So this is x squared over a squared. And we'll go ahead and plug that in for cosine of y. So dy dx is 1 over a square root 1 minus x squared over a squared. If I rewrite the a as the square root of a squared, then I can combine these square roots together. So I have a squared times 1 minus x squared over a squared inside the square root. And now when I distribute that a squared inside the square root, I'm going to have a squared minus x squared. So the derivative of arcsine of x over a is 1 over the square root of a squared minus x squared. That means that going backwards, if I was integrating 1 over the square root of a squared minus x squared dx, I would just get arcsine of x over a plus c. So this gives me an integration formula. Likewise, we can also show that the integral of 1 over a squared plus x squared dx is 1 over a arctangent of x over a, and the integral of 1 over x square root x squared minus a squared dx is 1 over a arcsecant x over a plus c. Okay, let's look at some examples. So in this first one, let's suppose that I want to integrate 1 over the square root of 4 minus 9x squared, integrating dx. If I try to do a u substitution where I let u equal the whole inside stuff, the problem is that I don't have any other x's to pair with the dx. So if we try u equals 4 minus 9x squared, then du dx will equal negative 18x. I can move constants over, so I could have negative 1/18 du equals x dx. But I don't have an x dx to substitute, so this isn't going to work. And there's no clever tricks or anything that I can do that'll make this work out nicely. Okay, so this doesn't work. Okay, what I want to do is recognize that this looks like one of our three inverse trig function integrals. And in particular, this first one, I have a squared minus x squared. Now, in this case, I don't have exactly x squared. I have 9x squared, but it's close. So we can say, all right, that looks close enough that I think that I can make that fit with a u substitution. Before I do a u substitution, let me just rewrite this. Instead of writing a 4, I'm going to write 2 squared. And instead of writing 9x squared, I'm going to write the quantity 3x that is then squared. Okay. And the reason that I want to write things this way is because my formula is a squared minus x squared. So I want a constant squared minus a function squared inside that square root. So my constant now, the a is going to be 2. And if I let u equal 3x, then this will be a u squared, and it'll fit the form of my integral. So du dx is 3, so 1/3 du equals dx. So let's go ahead and now substitute some things over. I'm going to leave the stuff inside the square root mostly alone. The 3x is going to become a u, and the dx becomes a 1/3 du. Okay. So now what we do is we say, okay, a is equal to 2, and I have the right form of my integral. 1 over a squared minus, there's nothing special about the name, it's like an x squared except we're calling it a u now, and we're integrating du. So I'm going to get arcsine of u over a. The 1/3 is a constant multiple, so it hangs out. Okay, so notice that it was 2 squared, so I have u over 2. It's not squared anymore because the a is just 2. And now we substitute back, and we get arcsine of 3x over 2 with the 1/3 out front plus c. Now going back to these formulas, sometimes it's easier if we reference them, in the way that you would see them written in the book would be, instead of writing x's, we could write these as a u. The integral of 1 over the square root of a squared minus u squared du is arcsine u over a plus c. Because when I'm doing an integration problem, this is how I'm likely to actually see the result. So for all of these, we could just write a u instead of an x. And we're not doing anything. There's no real work here. We're just changing the name of the variable. But sometimes when we're doing the actual problem, it's easier if things fit just nicely. Okay, notice that arctangent, tangent inverse, arcsecant, secant inverse, the same would be true with arcsine, sine inverse. They're all the same thing. You can use them interchangeably. Okay, let's look at another example. Suppose I want to integrate 5 over 9 plus 16x squared dx. To begin with, what I'm going to do is to notice that this looks like the form of an arctangent. The 5 is a constant multiple, so it can just hang out. And I'm going to let a equal 3 and u equal 4x. So then a squared is 9 and u squared is 16x squared. I have to be careful. We also have to convert the differential over. So du dx is 4. So 1/4 du equals dx. So the 5, I'm going to factor out of the whole integral. 9 is a squared. 16x squared is u squared. And the dx is 1/4 du. So now I'm integrating 1 over a squared plus u squared du. The 5 and the 1/4 are constant multiples. So then what I do is I say, all right, my formula says that's going to be 1 over a arctangent u over a plus c. So let's fill in what the a is. A is 3. The u is 4x. Okay, so we have 5/12 tangent 4x over 3 plus c. Okay, one last example. Suppose I want to integrate 1 over the absolute value of x times the square root of 4x squared minus 16 dx. I want to recognize that that looks like our arc-secant example. So here we're going to let a equal 4, so that a squared is 16. We're going to let u equal, well, another way to look at this is I want u squared to be 4x squared. So if u squared is 4x squared, if I square root both sides, u is going to be 2x. It's another way to figure out the a, or the u rather. And then I also need the differential, so du dx is 2, so 1/2 du is equal to dx. So the dx I can replace it with a 1/2 du. I have an x here, but u is equal to 2x, so this isn't equal to u. I have to solve this for x. And if I do, I get 1/2 u equals x. So I'm going to replace this x with a 1/2 u. So the 4x squared we said was u squared. 16 is a squared. We're in pretty good shape, but I'm going to do one more step. I'm going to take this 1/2 and I'm going to factor it out. It's a 1/2 in the denominator, so I can bring it into the numerator as a 2. This 1/2 I can bring out. So now our integral exactly matches an arcsecant, and the 2 and the 1/2 will cancel. So we get 1 over a arcsecant u over a plus c, and we substitute back. The a was equal to 4. The u is equal to 2x. And we could do an extra step here and simplify 2x over 4 as just x over 2. And there we have it.